Hi, my name is Paul, and I'm going to introduce you to a technique called independent component analysis, which we use in FSL for both pre-processing and analysis of resting state FMRI data. The implementation of ICA within FSL is called melodic. In this talk, I'm going to explain how ICA works and how we can apply it to FMRI data. In the next talk, I'll cover how we can use ICA to pre-process or clean up the FMRI data from a single subject. And in a later talk, I'll explain how we can use ICA combined with another method called dual regression to perform multi-subject analysis of resting state networks. ICA is an exploratory multivariate approach which we use to find hidden interesting structures that are present in our data. ICA produces a set of 3D spatial maps, each of which in principle represents one independent signal that is present in the data. The other main method that we cover in the FSL course is referred to here as network modeling. This is a complementary approach to ICA, which allows us to look at how the strength of functional connectivity varies between pairs of regions throughout the brain. The main output of ICA is a set of spatial maps, so in this way it's primarily a spatial approach. But with network modeling, we are more interested in the activity of different regions over time, so it's more of a temporal approach. Both of these approaches are covered in this course because they're complementary and they allow us to answer different questions about our data. In some cases, you may wish to use an ICA style approach, and in others it may be better to use a network modeling approach. Sometimes you may even use both. It really depends on the data that you have and the questions that you wish to ask. As we've already seen, for a task-based fMRI analysis, we start by setting up a design matrix, which contains explanatory variables, or EVs, that define the signals which we expect to see in the brain in response to our experimental stimulus. In a perfect task fMRI analysis, we would know exactly what we expect to find in the data. We encode every possible signal we might see as an EV in our design matrix. This would include task-based stimulus, and it may also include any sorts of confounds which we want to control for, such as physiological measurements. If we don't include every possibility in our design, our inferences may not be as strong as they could be. But in resting state, we don't have a task, so we don't have a time series model of what we expect to see, and we can't use a GLM-based approach. So you can think of task-based analyses as a confirmatory form of analysis. We have a prediction of what we expect to see, and we define a model from that prediction. Then the results that we get will depend on the quality of the model. If the analysis works, then they confirm the model. Whereas with resting state, we take more of an exploratory approach. We're searching for anything interesting in the data, and we don't constrain this search to a predefined model like we do in a task-based analysis. So let's step back for a moment and look at an fMRI analysis from a high-level perspective. We run an experiment to observe what a subject's brain is doing during a task or at rest. Then we use MR physics to make observations of this physiological activity. And then we can use software to analyze and interpret the data which we've acquired. And the point of this slide is to highlight the fact that there are many separate steps and separate stages in this process where variability or noise could be introduced and potentially will accumulate throughout the stages and could ultimately bias or corrupt our final interpretation. For example, at the experiment stage, our design may not be as efficient as it could be, or the subjects may not follow the instructions correctly. At the physiology stage, the timing of the hemodynamic response can vary across individuals and can even vary across the brain within one individual. At the physics stage, we have inhomogeneities in the magnetic field, which can cause signal dropout and other artifacts. At the analysis stage, we alter our data by resampling, smoothing, filtering, and interpolating it in various ways. I'm emphasizing all of this because for resting state, noise is particularly important. Remember that in a task-based analysis, we've defined a model of what we expect to see, and the GLM will take care of separating out our signal of interest, areas of the brain which activated in response to our stimulus and therefore which fit our model, from the signals that are not of interest, which is everything that we haven't specified in our model, all of the other sources of noise. And this is because we have a model of what we expect to see. In resting state, though, we don't have a model, and this means that the noise in the data can really dominate the signal that we're interested in, and therefore can dominate our final results. So we need to be particularly careful when we're pre-processing resting state data. So ICA is model-free in that we don't define an explicit time series model of what we expect to see in the data. However, internally, the ICA algorithm does use an underlying mathematical model which makes some assumptions about how to separate, how to find the hidden interesting structures and signals that are present in the data. And we will go into a little bit of detail, but not in any great depth, of these internals. You don't need to fully understand the details of how ICA works in order to successfully apply it to your own data. So I've already mentioned that ICA can be described as an exploratory analysis. It is trying to explain or represent the data by summarizing it. And it does this by decomposing or deconstructing the data into a collection of underlying features called components, each of which explains some part of the data. There are a number of other techniques which work in a similar manner to ICA, or which try to accomplish the same goal but in a different way, such as clustering, principal component analysis, or factor analysis. These approaches are all trying to accomplish the same thing, which is to deconstruct or decompose a complex data set into its constituent components, which are hopefully easier to interpret than the original data. But they all accomplish this task in a different way. ICA specifically searches for components which are maximally independent with respect to each other, and we will come back to the concept of independence in a little while. The tool which we use in FSL to perform ICA is called melodic. Melodic starts with a typical 4-dimensional fMRI dataset where the first 3 dimensions represent space and the 4th dimension represents time. We rearrange this into a 2-dimensional matrix where each row corresponds to a different time point and each column corresponds to a different voxel. So we work with a time by space matrix. ICA decomposes this time by space matrix into 2 more matrices. The first one containing a time course for each underlying component, and the second one containing a spatial map for every component that it has identified. And when this is finished, we can take each row of the 2D spatial map matrix and rearrange it back into a 3D image which we can then visualize. So this schematic may remind you of what we've seen in the general linear model, or the GLM, which we use in task fMRI. We have some data on the left and a time series model in the center, and we use the GLM to find a set of parameter estimates, beta values, on the right, which when multiplied by the model give us a good fit to the data. And conceptually, at a high level, ICA does use a similar equation to the GLM. The key difference is that with ICA, we don't need to define a model, which is X in the equation here. We don't need to define a design matrix before performing ICA. The ICA algorithm will actually estimate both the design matrix and the parameter estimates from the data. So let's look at an example. Let's say that we have an experiment which contains both a visual stimulus and an auditory stimulus. We run the experiment and we get some data which looks like this. Sometimes we see visual activation, sometimes we see auditory activation, sometimes we see both and sometimes neither. So how many features would you expect this data could be explained with? Well, first of all, we should see some sort of a background component which just contains the baseline signal, the baseline level of signal, and doesn't really contain anything interesting from our perspective. So we would hope to see a spatial map for this baseline component and an associated time course, which is just the mean. Next, we should see a component which represents the visual activity driven by the visual stimulus in our experiment. And finally, we should also see an auditory component, which represents the auditory activity. So this is what we can use ICA to do. We can use ICA to decompose our original data set into its constituent components. Although in practice, ICA doesn't actually give us a baseline component. Instead, this gets incorporated into the other components. So you can think of each component as a spatiotemporal summary of one part of the data, either visual or auditory in this case. And one aside, or an interesting point to remember is that these components can be linearly recombined to recreate the original data. So you can add the components back up and get your original data back. So the way that we use ICA on fMRI data is spatially. So melodic will output components which are as spatially independent as possible from each other, and will also, almost as a byproduct, give you the time courses which are associated with each of them. It is also possible to separate components based on temporal independence, but in practice, spatial ICA works much better on fMRI data and is therefore much more common. Performing ICA spatially will give us better results, basically because fMRI data has relatively high spatial resolution and relatively poor temporal resolution. In other words, we often have many more voxels than we have time points. So ICA has much more data to work with in the spatial domain and can therefore do a better job. So I've mentioned independence a few times, and I'm now going to try and explain what I mean by it. So in order to do this, it's useful to compare ICA with a related technique called PCA, or Principal Component Analysis. PCA is conceptually very similar to ICA, except that where ICA uses independence as its basis for separating components, PCA uses variance. So let's look at this example of a simulated fMRI dataset which contains two signals in it, and you can see the origin of these signals in these spatial maps. They're both in the visual part of the brain, they both overlap slightly, and one arises mostly from the left hemisphere and the other from the right. And you can see that they have very similar behavior over time, although if you look closely you can see that towards the end of the experiment the top time course starts to lag behind the bottom one by just this tiny amount. So what would happen when we apply PCA to a dataset like this? So I said before that PCA decomposes the data into components by analyzing variance. It will explain as much of the variance in the data as it can with the first component, and then each subsequent component will have the highest variance possible, remaining variance possible, under the constraint that it is uncorrelated or orthogonal to the preceding components. So for a dataset like this, you can see that PCA hasn't done a very good job of identifying the true underlying signals. The first component is explaining the average behavior of these signals, and the second component has captured the lag between them, which you can see is increasing throughout the experiment. PCA did a poor job with this dataset simply because the two underlying signals are too similar to each other. They're too correlated, and because PCA components explain variance which must be uncorrelated to the other components. Therefore it wasn't able to distinguish these two signals. Although if you look at it another way, PCA has actually done what it was supposed to do, which is to explain this dataset, or to decompose this dataset into constituent underlying parts. It's just that this particular representation that PCA has given us is not particularly useful to us. In contrast, what ICA will do when we give it a dataset like this is actually a much better job, because ICA doesn't work under this constraint of orthogonality, and therefore the fact that the two underlying signals are very correlated or are closely correlated with each other doesn't limit ICA, and ICA is actually able to identify the two signals. It separates them out spatially, and it also has been able to identify the time courses associated with them. So ICA gave us a much more useful representation of the data. So I said that PCA tries to explain data by assigning variance to each component, with the constraint that the variance explained by each component must be orthogonal or uncorrelated to the preceding components. And here I'm going to try and explain this visually with a simple two-dimensional data set. So we have two variables, x on the horizontal axis and y on the vertical axis, which are highly correlated with each other. And if we applied PCA to this data set, PCA would give us two components. The first component would be along the diagonal line where most of the variance is in this data. And because PCA has this orthogonality constraint, the second principal component would be at right angles to that first. And it would be capturing this small amount of residual variance along the main diagonal. So for a data set like this, PCA can actually do a very good job of explaining it. But PCA breaks down when we give it a more complex data set. So in this example, you can see that there's a much more complicated relationship between the two variables. And it looks like there's some underlying, or two underlying sources of variability in this data, which are not orthogonal to each other. Unfortunately, PCA wouldn't be able to pick this up because of its orthogonality constraint. If we applied PCA to this data, it would give us two components again, where the first component would be the average of the data along that main diagonal, which accounts for most of the variance in the data. And then the second component would be at right angles to that. For this type of data, ICA is much more useful because it uses higher order statistics, so it's able to identify the two primary signals in this example. So if two signals are independent, then they are by definition uncorrelated with each other. But if two signals are uncorrelated, they are not necessarily independent, as this example shows here. So again, we have two variables in this plot, x and y, and the correlation between x and y is 0, but you can see that there's obviously a relationship between them. If I know the value of one variable, then I can predict the value of the other one. This is what's referred to as dependence. Given knowledge about one variable, then I can tell you something about the other. The key to two variables being independent is that given knowledge about one variable, I can't tell you anything about the other. There is no shared information between the two variables. This is something that correlation can't do and PCA can't do either. But because ICA uses higher order statistics, it can be used to work with data like this. So as an example of a higher order statistic, if we simply took the square of this data set, then this would make the relationship between the two variables linear and much more easier to analyze. So now I'm going to try and explain ICA in a different way. We're going to think about ICA as a tool for unmixing a mixture of signals. So here we have 4 different sounds, and I'm going to play them one by one. Here's the first. And the second. And the next one is very unpleasant. And then the final sound. So I want you to think of these sounds as 4 true underlying signals which are in our data set. And if we recorded these sounds simultaneously from 4 different microphones, each microphone would record a varying mixture of those 4 underlying sources. And looking at these mixtures, it would be very difficult, given one of them or given all of them, to disentangle an individual underlying source. If we listen to one of these mixtures, however, then as humans, our ears are actually capable of identifying individual parts of each of the 4 underlying sources. And we can clearly see that there are different underlying sources which are present in one of these mixtures. And this is what we want to use ICA to do. We want to give ICA these mixtures, and we want ICA to decompose the mixtures and to give us back those underlying sources. So this is directly analogous to fMRI data, where each voxel contains a time series which is composed of a number of underlying sources, be those sources true neurological signal or noise of some sort. And we want to use ICA to unmix those voxel time series and to reconstruct the original sources. And the way that ICA does this is by looking at the distributions of the signals and the distributions of the mixtures. So if we look at the distributions of the underlying signals on the left, we can see that they're all very different, but they have one critical thing in common, which is that they are all non-Gaussian. None of them looks like a nice, smooth, normal distribution or bell curve. In contrast, if we look at the observed data, which each contain varying mixtures of the original signals, you can see that they all look much more Gaussian than the signals. And this is due to something that you probably have heard of before called the central limit theorem, which in this context is simply saying that the more you mix things together, the more Gaussian they become. So ICA does something clever with this central limit theorem by turning it around and saying that if we separate our observed data so that it is as non-Gaussian as possible, then it is unlikely to be just a random result and more likely to be a true underlying signal. So all we need is some measure of non-Gaussianity which we can optimize to find our underlying signals. There are a few different ways to measure non-Gaussianity, and in melodic we use something called negative entropy. So this is one of the critical assumptions that ICA makes, which is that the true underlying signals which we're interested in are non-Gaussian, and generally this is a fairly safe assumption to make. So for those of you who are interested in the gory details, ICA uses a measure of independence as a cost function within an optimization routine to find an unmixing matrix, which when multiplied by the input data produces components which are as non-Gaussian as possible and therefore as independent as possible. And in melodic, which is FSL's ICA implementation, we use negative entropy for the cost function and fixed point iteration for the optimization routine. So hopefully you have a better understanding of how ICA works. In the next few slides, I'm going to talk about a few practical issues that we need to address when we apply ICA to FMRI data. The first problem is overfitting, and then the next one will be thresholding. So a practical consideration of using ICA is that the algorithm does not know what is a true signal or what is noise, and even more importantly, it doesn't know how many true signals are present in the data. Therefore, if we apply ICA in an unconstrained manner, it will typically decompose the data into many more components than there are actually true signals present. This results in individual underlying signals being split into many separate components. This is referred to as overfitting. For example, imagine that we run a task-based analysis which triggered the activations shown in the bottom left. An unconstrained ICA analysis would potentially split this activation blob into a set of smaller and smaller components, each of which would be more difficult to interpret than the original data. And this would defeat the purpose of using ICA in the first place, because remember, we're trying to make our data more interpretable, not less. We can do a few things to get around this overfitting problem. The first step is to add an extra noise parameter to our ICA algorithm. So we're still trying to decompose our fMRI data into a set of spatial maps and time courses based on independence. But now we can use this extra noise term, which can be used to soak up some parts of the data which cannot be well explained. But now we need to figure out some way of telling ICA how many components to use in order to best explain the data and to not overfit by explaining this noise. This is referred to as the model order selection problem. To explain this a little bit more, given a data set like this, we can see some really interesting patterns of activity. But how do we determine the optimal number of components that should be used to describe the data? If we split the data into too few components, we're unable to capture all of the signal that is present, or each of the signals that are present in the data. Similarly, if we specify too many components, then the true underlying signals will be split up into many smaller components, each of which become harder to interpret. So we need some way to figure out the optimal number of components to split the data into, which best explains each true underlying signal and is most easily interpretable. And this model order selection problem is one of the main challenges in ICA. Melodic has a built-in feature which you can use to automatically estimate the model order. To do this, Melodic actually begins by starting with a PCA. So recall that when we do a PCA, the first component will explain the most amount of variance in the data, the second component the second most, and so on and so forth. So in a typical data set, we would expect to see the variance explained by each component to look like the green line, where the first few components explain most of the variance in the data, and then the explained variance drops off in the remaining components. We can also figure out what this plot would look like for a data set which is made purely of noise. It would look more like the dashed blue line, where there is not much difference between any of the first few components in the amount of explained variance, so we don't have that characteristic drop-off that we would see in real data. And what Melodic does is it looks at the difference in the amount of explained variance by the components in our actual data set, the green line, and the amount of explained variance in an equivalent random data set, the dashed blue line, to determine the best number of components that can be used to explain the data. And at the point where the green line meets the blue line, the components from our real data set are effectively explaining the same amount of variance that would be present in a random data set. So we can assume that at this point that all of the remaining components are just noise and we can throw them all away. So this is what Melodic does to define the optimal number of components or model order for our data. So we've dealt with overfitting and the model order selection problem. We used a PCA to reduce the dimensionality and also to decide how many components to split our data set into. And now we've used an ICA to separate out those components based on maximizing independence by measuring non-Gaussianity. And this process will end up giving us something like the spatial map on the top here, one spatial map for every component. These maps have a value at every voxel in the brain. Voxels which contributed strongly to the component have high values, and voxels which didn't have much to do with the component have low values. But now we need to figure out some way of thresholding these component spatial maps so that we can decide with some level of certainty which regions of the brain are involved in the component, which regions of the brain are actually driving this true underlying signal, and which regions are not. And again, we're going to solve this problem by looking at distributions, the distribution of the component data. So the distribution of a component spatial map will typically look something like this. We can see a large peak centered around 0, which contains all of the voxels which did not contribute very much to the component. But there is a smaller peak off to the right containing high values, and these are the ones which contain interesting voxels that form most of the signal in this component. And hopefully you can see that because this is not normally distributed data, we can't use a standard statistical test like a t-test. Instead, we need to do something a bit more advanced called mixture modeling. In mixture modeling, we assume that the data is made up of a combination of distributions, and where a classical statistical test tries to fit a single Gaussian distribution to the data, in mixture modeling we fit multiple distributions. So for each component spatial map, we use one distribution to model the noise, the big peak containing all of the uninteresting voxels, and then we use a second distribution to model the smaller number of more interesting voxels off to the right. A third distribution may also be used to model negative values, although in this particular example, 2 distributions are enough. And once we've fit these distributions, we can say for each voxel how likely it is to be in the noise part or in the signal part of the component. There's one more technical issue which we need to consider when applying ICA to FMRI data. So you recall that ICA extracts spatially independent components. This means that ICA tries to maximize the spatial independence so that there is as little similarity in space between components as possible. Intuitively, though, this doesn't sound like a very good approach, because we know that a single brain region can be involved in many different networks of activity. So if we're trying to make our components as spatially independent as possible, how could the involvement of such a region of integration in different networks be captured? Well, in practice, it turns out that this is not a problem. So as an example, let's say that we have some data which looks like this, very boring. These black squares represent the brain, and the white rectangles represent some sources of activity within the brain. And we want ICA to extract these two sources as independent. You can see, though, that these sources overlap spatially by quite a bit. They are actually spatially correlated by 50%. And to be honest, if we had data as clean as this and we gave it to ICA, it wouldn't do a very good job of separating out the two sources. But remember that fMRI data is extremely noisy, and in this situation, noise works to our advantage. If we add a typical amount of noise to this simulated data, the spatial correlation between our two sources drops right down to 10%. And the presence of this noise means that ICA is actually able to identify the two sources as spatially independent components. And once we apply our mixture modeling and threshold these component spatial maps, we get pretty good results, which have done a fairly good job of capturing the two true signals which are in our data. So hopefully you now have a working knowledge of how we can apply independent component analysis to fMRI data. We can use it to split the data into a collection of underlying components which are easier to interpret than the original data. And now that the theory is out of the way, in the remaining talks I'll explain how we can actually use ICA to do something useful. In the next talk, we will apply ICA to the fMRI data from a single subject as a pre-processing step in order to separate true neuronal signal from all of the noise that we know is present in fMRI data. And then in the later talk, we will use ICA at the group level to identify whole brain resting state networks, which we can use as the basis for group analyses. Okay, thanks for listening.